Assalamualaikum warahmatullahi ta'ala wabarakatuh. Welcome to another video on MCTE 2311 Signals and Systems Analysis. In this video, I will talk about inverse Laplace transform. Okay, so let's assume that you are given a signal, okay, f of s like this. Okay, 2 over s squared plus s plus 5. And then you are asked to determine the equivalent of this signal in time domain. Okay, so this signal in, you have the s variable here, so means this signal is in the frequency domain. You are asked to determine the equivalent in the time domain. Okay, so you can do that by applying the inverse Laplace transform. Okay, so denoted by this capital L to the power of minus 1. So the inverse Laplace transform can be used to convert our function or our signal or our system from the frequency domain to the time domain. Okay. So a mathematical method known as partial fraction expansion is used in order to do the inverse Laplace transform. So in this video, I will discuss 3 cases on how this Fs, this signal, can be expanded into partial fractions depending on the roots of the denominator. Okay, this is the denominator of Fs. So for case number 1, if you have the roots of the denominator of Fs real and distinct. Okay, for example, let's say you are given a signal like this, Fs equals to 2 over s squared plus 3s plus 2. So if I modify this signal, I can get Fs equals to 2 over s plus 1 and s plus 2. Okay, so here the roots of the denominator are real and distinct, which is s equals to minus 1 and s, let's say s1, s2 equals to minus 2. Okay, so when you have the roots real and distinct, okay, the next thing to do is do like this. Okay, I think you have learned this in your mathematics course as well when you study inverse Laplace transform. So you can take this as revision. Okay, so since you have 2 distinct roots, so you will have k1 over s plus 1 plus k2 over s plus 2. So what I usually do, okay, I will multiply this k1 with s plus 2, multiply this k2 with s plus 1, so that the denominator is equals to this. Okay, so when I arrive here, I usually put like this. I'm sure there are different methods to which you can solve this. Okay, you might learn from your mathematics course. So you can use whichever method that you feel comfortable with. But this is the method that I always use to teach my student in my class. Okay, so once we have the denominator equals, okay, now we can write the numerator only. And you have to multiply this inside. Okay, so here we have 2 equals to k1s plus 2k1 plus k2. Okay, now we can do like this. Okay, since we have s to the power of 1 is the highest s, so we write here s to the power of 1, s to the power of 0, which is equivalent to 1. Okay, so on the left hand side of this equal symbol, we don't have any s. Okay, so is equals to 0. Equals to, now on the right hand side of this equal symbol, we have k1s and k2s. Okay, so you write k1 plus k2. I wish if you arrive here, you will get k1 equals to minus k2. Now for s to the power of 0, which is 1, okay, so here you have 2. So you write down 2 equals to, and here you have 2k1 and k2. 2k1 plus k2. So from here, you can write 2, k1 is minus k2, so minus 2k2 plus k2. So here you will get k2 equals to positive minus 2. Okay, so k1 equals to 2, right? So you can write back the fs, which is equals to k1 over s plus 1. Okay, so 2 over s plus 1 plus k2 is minus 2 over s plus 2. Okay, so this one I can simplify further. So it will become 2, 1 over s plus 1 minus 2, here 1 over s plus 2. So once you arrive here, okay, you can perform the inverse Laplace transform of this part, the one in the bracket, okay, using the Laplace transform table. Okay, so you can check in one of the slides that I used to discuss introduction to Laplace transform. So f of t equals to 2. So this one is similar to e minus t. Okay, minus 2e minus, because you have 2 over here, so it's minus 2t. And the whole thing multiply with ut. Okay, so this is the inverse Laplace transform of the function fs here. Okay, now let's have a look at, okay, so this is the general form. Okay, if you have the denominator of fs real and distinct. Okay, so this is how it looks like. So you have p1, p2, which are the roots, okay, of the denominator of fs. Okay, so depending on how many roots you have, you will have this multiplier, okay, k1, k2 until kn, depending on the number of roots that you have. So this k is just a variable, so you can use any symbol, a, b, c, okay, whatever that suits you better. For case number 2, if you have a real and repeated roots, okay, for example, as shown here, this s plus 2 is to the power of 2. So it means you have s plus 2 repeated 2 times. Okay, which means the roots of the system is s1 equals to minus 1, s2 equals to minus 2, s3 equals to minus 3. Okay, so later when you study control system, you will see that actually your system, okay, it means that you have 2 poles at minus 2. Okay, so you have 1 pole at minus 1 and you have 2 poles at minus 2. Okay, so that's what this means. So this is minus 2. Okay, so when you have the denominator with repeated roots like this, okay, so you write fs equals to 2 over s plus 1, s plus 2 square. Okay, now you will have k1 over s plus 1 plus k2 over s plus 2 plus k3 over now s plus 2 square. Okay. So again, my method, okay, I will make the denominator of this k1, k2, k3 equal. Okay, so you will have 2 square. Hope it's not too difficult to read the handwriting. So here you will have k1. Okay, so to make the denominator equals to here, you have to multiply k1 with s plus 2 square plus k2, you have to multiply with s plus 1 and s plus 2. For k3, you have to multiply with s plus 1 over. So now the denominator are the same with this one. Okay, so we can write now the numerator only, which is 2 equals to, now you have to expand this and multiply with k1. If you do that, you will get s square k1 plus 4 k1s plus 4 k1 plus k2s2 plus 3 k2s plus 2 k2 plus k3s plus k3. Okay. So here the highest power of s is to the power of 2. So we start from s to the power of 2, s to the power of 1, and s to the power of 0. Okay. So here on the left hand side of the equation, we don't have s to the power of 2. So we write 0 equals, over here we have k1. The multiplier of the s square is k1. And here we have k2. For s1, similar s to the power of 1. Similarly, on the left hand side, we don't have any. So we put 0 equals to, over here we have 4k1 plus multiplier of s here, 3k2 plus, we have one more here, k3. So for s to the power of 0, which is 1, we have here 2. Here we have 4k1 here. And 2k2, k3. So once I arrive here, usually I just take my calculator and find the solution to these 3 equations. Okay, you can do that with your calculator. I hope you know how to do that. So you will get k1 equals to 2, k2 equals to minus 2, and k3 equals to minus 2. Okay, so now you can rewrite the equation so that you have fs equals to, k1 is 2, so 2 multiply with 1 over s plus 1, k2 is minus 2 over 1 over s plus 2, K3 also minus 2. S plus 2 square. Okay. So if we do the inverse Laplace transform of this individually, okay, so you will get f of t. Now if you remember, let me just try if I can change this. So if you remember in our table, in the Laplace transform table, okay, when you have e minus at ut, then the Laplace transform is 1 over s plus a. And if you have t, if you have t ut, then the Laplace transform is 1 over s square. Okay, so this one, this number 1 and number 2 are familiar with this one. Okay, so you have 2 e, since you have positive here, so you will have negative, and the a is 1, so minus t, minus 2e. This one, the a is 2 and positive, so you will have minus 2t, minus 2. Okay, now here you have 1 over this square, which is equivalent to this s square, right? But you have this s plus 2, which means you have a frequency shift. Okay, so you will have t, and the frequency shift is e. If you still remember, when we have a frequency shift, ESO of t, ft, okay, then the Laplace transform, you have f of s minus s naught, okay, which is this s naught. So you will have e here. Since you have positive 2 here, means you will have here the s naught is negative 2t. Okay. And the whole thing is multiply with u of t. Okay, so this is the inverse Laplace transform of this equation. Okay, so in general form, okay, if you have real and repeated roots, okay, for the denominator of fs, so this is the repeated part. Okay, so you will have the partial fraction like this. Okay, where you have the repeated roots here, you have to repeat. Okay, start from the order, and then minus 1 until to the power of 1. Okay, and then you write down the other roots. So for case number 3, if you have complex or imaginary roots, how are you going to solve that? For example, let's say you are given this equation. So this is the complex part. Okay, if you try to solve this, you will get the complex roots or the imaginary roots. Okay, so the first thing to do is similar like before. Okay, so you write down f of s equals to 3s plus 5. So here you will have k1 over s plus, now for this part, it will be k2s plus k3 over s square plus 2s plus 5. Okay, so similar like before, what I will do is make the denominator equal. If you make the denominator equal, you will have 3 equals to this k1 multiply with this part, s square plus 2s plus 5, and this K2s plus K3, you multiply with s. So you have the denominator equal. Now we can write the numerator only. And this one you multiply inside. I get K1s square K2s square plus 3s. Okay, so the highest order of the s is to the power of 2. So we have s2, s power 1, s power 0. So on the left hand side, we don't have s to the power of 2. So we write 0. Here we have K1 plus K2. Similar for this one, 0 equals to, we have 2K1 plus K3. And for this one, you have 3 equals to 5K1. Okay, so from here you have K1 equals to 3 over 5. So from here, if you solve, you will have K2 equals to minus 3 over 5. And from here, you will have K3 equals to minus 6 over 5. Okay. So if we write back the equation in terms of the partial fraction, we will have 3 over 5, 1 over s, plus, this is minus 3 over 5, s, minus 6 over 5, over s squared plus 2s plus 5. Okay, which this one can be simplified, so you can get fs equals to 3 over 5 over s. This is minus 3 over 5. So you'll have here s plus 2. Here is s squared plus 2s plus 5. Now this form here, the one is inside the bracket here, is equivalent to this. Okay, so equivalent to this equation in this red box here. Okay, as plus b over s squared plus 2as plus c. Therefore, the inverse Laplace transform, okay, inverse Laplace transform of this part, okay, the inverse Laplace transform of this part is equivalent to this equation. Okay, we can use this equation where r is equivalent to this, theta is this, and b, the small b, is this formula. So this is actually known as the using the trigonometric identities of sine and cosine function. Okay, so if we solve this, okay, this equation, you have your capital A, let's write here, capital A is equals to 1, which is the multiplier of s. So you have 1, capital B equals to, here, 2, and here 2a s equals to 2s. 2a equals to 2, so your small a equals to 1, and c is this one. Okay, so you have c equals to 5. Now b, if you substitute here, okay, square root of 5 minus 1, so it's square root of 4, so you get b is 2. So now you can calculate r. You substitute all the values. You will have 1 square multiplied by 5, then plus 2 square minus 2, 1, to 1 over c minus a square. So it's 5 minus 1 square. So you get r equals to 1.118. Okay. If you substitute theta, which is arctangent, this capital A, small a minus capital B over capital A, which is 1, square root of c. 5 minus small a is 1 square. This one you will get arctangent of minus 1 over 4. So you will get minus 26.56 degree. Okay. So if you put everything, okay, the inverse Laplace transform of the original function here, okay, is equals to 3 over 5 is 0.6 and 1 over s is u of t. And you have this over here, minus 3 over 5, which is also minus 0.6. And then multiply by the whole thing here, which is this equation. So r is 1.118, e small a is 1, so minus t cos small b is 2, so you will have here 2t plus theta. So there is 2t minus 26.56 degree. Okay. U of t. Okay. So your f of t equals to 0.6 minus, if you multiply this, you get 0.671 e minus t cos 2t minus 26.56 degree, the whole thing, u of t. So this is the inverse Laplace transform of this function f of s. Okay. And this is if we are using the method known as trigonometric identities of the sine and cosine function. But there are other methods that you can apply, okay, in order to find the inverse Laplace transform of complex or imaginary roots. Okay, which I think you have learned in your mathematics courses. So in the general form, if you have a complex or imaginary roots, the partial fraction expansion is given by this equation. Okay, so here is the imaginary part. Okay, so for the partial fraction expansion, you have it like this, in this form. Okay. Right, so I will see you in the, another video where I will discuss how to solve a differential equation using Laplace and inverse Laplace transform. Thank you.